Hello again. This is video lecture 27.3, and we're going to talk about section 3 in chapter 27, which is all about the topic of the latest experiment you're working on, what's called an RC circuit. And that's just a way that physicists refer to circuits that have resistors, that's the R, and capacitors, that's the C. Of course, there also has to be some kind of energy source, like a battery or a power supply. But that's the key thing. It's got a resistor, or multiple resistors, and a capacitor, or multiple capacitors. So we're going to analyze the circuit you see on the top right here. It really consists of three elements: a battery with a source of EMF and the polarity shown, a mechanical switch, S, a resistor, and a capacitor. So four things. Just like the circuits you've been working with in lab. And initially, this capacitor that you see there has no charge at all. Okay, it's initially uncharged. And when we're ready, and we're going to call it time zero when we do this, we're going to throw this switch S so that it makes a connection with point A by just pushing that line up. Then we will have a closed loop consisting of the EMF, the resistor, and the capacitor. And the EMF will do work on positive charges and make current, and that will start charging up the capacitor. And the plate here will end up getting positively charged, and the lower plate will end up becoming negatively charged. And we want to be able to analyze that process, okay? We're going to also just assume some numbers for these circuit elements. The capacitance, 1 microfarad. That resistance R, 2,000 ohms. The EMF of the battery, ideal battery, 10 volts. And I'll explain what that next symbol is in just a minute. All right, so I'm going to point out how we analyze this circuit. And there is, in fact, absolutely no new physics here. We are just going to use several physics ideas that we've already talked about. And one of those ideas will be the loop rule, conservation of energy. I'm going to pick a point in the circuit. How about point A? Right there. And I'm going to become a circuit inspector, and I'm going to do one traversal, one loop around the circuit until I get back to point A. I'm going to traverse the way the current would be flowing in this circuit. Do you see which way that would be? Look at the arrow on the EMF. The current I that's flowing in this circuit is going to be going around clockwise, like that, around that outer loop. Once I have thrown the switch up to point A, it made a closed loop. Okay, so I'm going to start at point A, and I'm going to go with the flow as a circuit inspector. I'm going to go clockwise. I'm going to take all the potential gains as pluses, all the potential drops as minuses, and when I get back to point A, the grand total must be 0. All right, let me write that down then over here on the far left. What do we get when we apply the loop rule to this outer loop right here? Right like that. Starting at point A. Nothing happens until we go through the resistor, and then we go with the flow. So when you go through a resistor with the flow, that's always a potential drop of I times R, so minus IR. Then we come across the capacitor, going from the positively charged plate to the negatively charged plate. And we know that when we charge up a capacitor, remember the physics of chapter 25, that whole chapter was about capacitance, that we're building up an electric field, E, in the region between the plates. And that electric field points away from the positively charged plate towards the negatively charged plate. So in that region between the plates, the electric field points downward. And the electric field points in the direction of decreasing electric potential. So as I traverse the loop from the positively charged plate to the negatively charged plate, that's a potential drop. So in the loop rule, that'll be a minus. By how much? Whatever the potential difference is across the capacitor. I'm just going to put that like that because that's going to be changing with time, getting bigger and bigger as the capacitor gets more and more charged. All right, that's the capacitor. Then we go around the bottom part, which is just conducting wire. And then we go up on the left side through the battery in the direction of the EMF arrow. So that's again plus curly E. And then I get back to point A, so that's where I started. So the total must be 0. That's the loop rule to that outer loop. Now I do add one more piece of physics. Now, it's that potential drop across the capacitor. Chapter 25 taught me that the governing equation for a capacitor is Q equals CV, where the V means the V across the capacitor. So that's what I'm going to use. Now rearrange that. V is Q over C. So this is minus IR minus Q over C plus EMF must equal 0. And then I'm going to use another bit of physics from chapter 26. That current at any point in a circuit, by definition, is the rate at which charge is transported at a point, dq dt. And I'm going to replace that I with dq dt in the first term. So that term becomes negative R times dq dt minus Q over C plus curly E must equal 0. And I will just rearrange this a little bit and get the dq dt part by itself. So minus R times dq dt equals Q over C minus EMF, or dq dt equals E over R minus Q over RC. As you can see it. And that is the equation right there. Might look kind of odd, but that is an equation that will tell us the charge on the capacitor plates. And it's a function of time. In fact, what this is called, that this equation I just highlighted, it's called a differential equation, because it's got a derivative in it. And it tells us that the rate of change of Q, that's the quantity on the left, is determined by the EMF, the resistance, the capacitance, and the Q itself. And so when you have a differential equation for a variable, in this case Q, you want to solve it. And when you solve that equation, you would get the Q, the charge on the capacitor, as a function of time. And that's what we want to do. We want to get Q as a function of time. Okay, so now that I'm at this point, this is what the loop rule has obtained for me, this differential equation. I need to solve it. I will tell you that the next bit I'm about to do is not something that you would be asked to do on a homework or a quiz or an exam. And so you are, if you wish, allowed to skip over the next part. But if you're curious as to how to solve this differential equation, I'm going to show you how you do it. All right, so this next part is purely for those who want to know mathematically how to solve this differential equation. So I'm going to come down here to this blank space, and I'm going to explain about solving the differential equation for the charge on the capacitor as a function of time. It requires us to know one thing that's called an initial condition. What is happening to the charge at time 0? Q at time 0. Well, the capacitor is initially uncharged. It has no charge. So the initial Q will be 0. All right, so you see the differential equation up there. It's highlighted. It's called a first order ordinary differential equation, first order differential equation, because it's got a first derivative in it. How do we solve it? The technique I'm going to use is called separation of variables. And the way it works is, let me think of that diff EQ written in this form. dq dt equals, bracket, EMF over R minus Q over RC times 1. That whole quantity in the brackets times 1. And then what I want to do is cross multiply. I'm going to take all this stuff in the brackets on the right over to the left and downward. And I'm going to take this dt over to the right and upward. So that then the next step looks like this. dq over E over R minus Q over RC equals 1 times dt, or dt. And then I integrate both sides. So integral on both sides. Doing the same thing to both sides, you can do that. And I put limits on these integrals. The time integral on the right, dt, well, time starts at 0, and then the upper limit is some arbitrary time t, whatever t we're interested in. The integral on the left is with respect to charge, dq. So the limits have to be charge values. And specifically, the lower limit has to be the charge when the time is 0. But the initial charge is 0. And then the upper limit is the charge when the time is t. So I'll just denote that q of t. Okay, now the integral on the right is easy. The integral of dt from 0 to t is just t. So that's done. The only integral that we have to work at is the one on the left. How do we tackle that integral on the left? I'll do a u substitution. Let's let u, new variable, equal e over r minus q over rc. Now keep track of what's a variable. Q and u are variables. E and r and c are constants. Then I take the differential of both sides of that expression, du. Remember, e and r and c are all constants. So du will be negative dq over rc. Or to rearrange that, dq equals negative r times c times du. Make sure that's visible. Okay? And then let me substitute that expression right there. dq, minus r times c times du. That expression right there for dq, up there in the top. All right, so now let me continue over here. What do I have on the left? I can bring the negative rc out front of the integral, and then I have du over u. And then what do I have on the right side? Just a t. Oh, that's a little bit too high. There you go. Now let's put the limits on the left. They're u values now. But their u values are not hard to figure out, because you go to the defining expression for u, right there, and you plug in the lower and the upper limit for q. So to get the lower limit on u, put in the lower limit on q into that formula for u. The lower limit of q is 0. So the lower limit for u, the initial value of u, is e over r. And the upper limit for q is q of t. So the upper limit for u is, don't really have a lot of room here, e over r minus q over rc, where that q is q of t. Then that's a famous integral right there, du over u. That's the natural logarithm of u. This is minus rc, natural logarithm of u, between these limits. And then that's minus rc times natural log of e over r minus q over rc minus natural log of e over r is equal t. Then use property of logarithms, that I can write that as natural log of e over r minus q over rc all over e over r is equal t. Now divide both sides by negative RC, and you get natural logarithm E over R minus Q over RC all over E over R equals negative T over RC. Remember, the whole point is to solve for Q. There's the thing right buried in there that I'm solving for. So to get that, I got to get rid of the logarithm. Well, the inverse of the logarithm is the exponential. So I take the exponential of both sides. And this left-hand side just becomes E over R minus Q over RC all over E over R. And now here on the right, I have E to the minus T over RC. And now the next little bit I'm going to let you do. You do the algebra carefully to solve for that Q. And I'm going to write down what you get. You'll get Q, and it's going to be a function of T. You get C times the EMF times 1 minus E to the minus T over RC. That's a pretty famous result for the charge on a charging capacitor as a function of time. And now you have seen a solution to a differential equation. Now, this is where the little aside stops, and we're back to stuff you do have to be able to do. Because now that I've shown you what that result, I'm going to go back up to this slide and point out that that result is right here in the middle of the screen. Okay? The charge on the capacitor as a function of time equals C times E, curly E, the EMF, times the quantity 1 minus the exponential to the minus T over RC. And now what we have to do is we have to graph that. And one of the things I'm going to point out is something that's not at all obvious. But it is true that the argument of an exponential must be a dimensionless quantity. So that combination there in the exponential function, the T divided by RC, has to have no units. That means the combination of R times C, resistance times capacitance, must have the dimensions of time, and in SI, units of seconds. And so that combination R times C is called the time constant of the circuit. And there's a special symbol for that time constant. And it's the Greek lowercase letter tau, not a T, tau. Now for this circuit we're studying, remember the R is 2,000 ohms and the C is 1 microfarad. So the time constant tau, R times C, which is now written over here, turns out to be 2 milliseconds, or when expressed in SI, 0.002 seconds. All right, so now let's see the graph of the charge on the capacitor as a function of time, Q. It's going to be graphed here in microcoulombs, and the time's going to be in milliseconds, because that's convenient. And the graph is this green curve. All right, first let's plug into this formula here, time 0, and see what the Q formula is, okay? All right, let me get myself some space over here so that we don't have too cluttered of a screen. And we just take this formula right here and we ask, what does it give when we plug in T equals 0? I mean this formula right here. Well, you plug in T equals 0, you've got a 0 right there. E to the 0 power, anything to the 0 power is 1. But that's inside a parentheses, and it's 1 minus that. Well, 1 minus 1 is 0. And 0 times C times the EMF is still 0. So the initial charge is 0. And sure enough, the graph at time 0 starts with a Q of 0, right down there. And then it smoothly rises. Let's imagine the limit as the time gets huge. The physicist would write that like that. Let the time go to infinity. And then see what the formula gives. So now we're imagining the limit where that T is approaching infinity. Notice then that what you've got for the exponential is the exponential at minus infinity. Now, if you just think of the exponential function by itself, negative exponential, e to the minus t over rc, it just decays towards 0, right? A negative exponential function just decays asymptotically towards 0. So e to the minus infinity is 0. And 1 minus 0 is 1. And 1 times c EMF is c EMF. So the final charge on the capacitor is just c times the EMF of the battery, which is the thing that's charging it to begin with. Okay? And c times E, for the numbers we're given here, is 10 microcoulombs. And so you see an asymptotic line dashed here at 10 microcoulombs, which is the value of c times E. And then the curve just smoothly grows from 0 and asymptotically approaches c times E. Now, remember the product of R times C is called the time constant for the circuit. That combination of R times C, which in this case has a value of 2 milliseconds, is telling us the time scale over which the charging occurs. The time constant is 2 milliseconds. And so what this graph does is it marks in 2 millisecond intervals the little diamond down here on the time axis. See the first one at 2? That's at 1 time constant. And when you're at 1 time constant, Q at t equals tau, remember tau is just R times C, the formula for Q is that, because you plug in for t the value tau, which is RC, and you're just getting e to the minus 1. And you do 1 minus e to the minus 1 in your calculator, and you'll get that this is about 0.67 of E. I meant to say 0.63 of E. Okay? So at 1 time constant, when you're roughly here on the graph, you're at about 63% of C times E, the final charge. And then next, they've got a little tick mark at 4 milliseconds. Well, that's 2 time constants. And then you're at C curly E times 1 minus e to the minus 2. Let's see what that is. You're at 2 time constants. That's about 0.86 of C times E. So that's right here. You're at 86% of your final charge, and so forth. Notice after, there's the 3rd time constant, 2 more milliseconds, and then there's the 4th, and there's the 5th. Certainly after 5 time constants, you're so close to the final charge on the capacitor that most people would say, hey, it's charged. So that's how the capacitor charges with time. Now there's more to the circuit than that. How about the current I in the circuit as a function of time? That you calculate by just taking dq dt, where the Q is the Q formula right up above. Okay, right here. Here's the Q. Take dq dt. Remember, C times E is a constant, 1 is a constant. You have to use the chain rule. When you take dq dt, you'll get C times E, and then from the E exponential, you think of that as e to the blob. You'll have e to the blob times the derivative of the blob with respect to t. That'll leave you e to the minus t over rc, that may be hard to see, and then a 1 over rc, and the factors of c cancel, and you're left with e over curly e over r times e to the minus t over rc. Let me write that formula over here to the side, because it's plotted right here. The current in this circuit as a function of time is the EMF over the resistance times the exponential of minus t over rc. Now that's just a plain old exponential decay. Note the initial current, plug in time 0, is e curly e over r, and e to the 0 is 1. It's curly e over r. And that turns out to be, using the EMF as 10 volts and the R as 2,000 ohms, 5 milliamps. And that's this point right here on this graph, where I is in milliamps. All right, and then again, we've got on the time axis little tick marks at intervals of a time constant, 2 milliseconds. So after one time constant, t equals 2 milliseconds, what's the current in the circuit? I at time tau. That's curly E over R exponential to the -1. That's roughly 0.37 times E over R. But E over R, curly E over R, was the initial current. So we're at one time constant, we're about at 0.37 of the initial current, which was 5 milliamps. So we're about 1.85 milliamps, and that's right about there. And then after 2 time constants, we're even less, and so forth. And certainly after 5 time constants, the current in the circuit is essentially 0. So while the charge on the capacitor is growing exponentially and approaching an asymptote, the current in the circuit is just decaying exponentially. All right? Very famous behavior. One more thing that's often useful to know. What's the potential difference across the capacitor as a function of time? In other words, what if we were to have put right across the capacitor the leads of a voltmeter and measure the potential difference in volts across the capacitor? What would it be? Well, remember Q equals CV for a capacitor, but the Q is changing with time, so the potential difference across the capacitor is changing with time. And since the Q is growing, the capacitor is charging up, the potential difference is growing. And it's not hard to get what that formula is. Let me clear some of the stuff away so we don't have this distraction here. Okay. What is the potential difference across the capacitor as a function of time? V capacitor. Take the charge on the capacitor divided by C. Q equals VC. Here's the formula right over here to the right for the charge. C times the EMF times 1 minus the exponential minus T over RC. So divide that by C. The C's just cancel out, and you get this formula. EMF times 1 minus e to the minus T over RC. So if we plotted VC versus time, or sketched it over here, just a sketch, at time 0, I have 0. As time approaches infinity, I approach an asymptotic value of the EMF, and then it just smoothly grows towards that. Okay? All right, now let's look at this formula for the potential difference across the capacitor in 2 extreme limits. Initially, at time 0, we'll just plug in time 0 into that formula, and like I said, you get 0. So initially, when the capacitor is uncharged, there is no potential drop across it. Well, that's just like a plain old conducting wire would behave. So here's a very useful thing to remember when you're trying to understand how a circuit with a capacitor will behave. If the capacitor is uncharged, the capacitor acts like what we call a short in the branch where the capacitor is. That means just like a plain old conducting wire. Just like in that circuit, if I drew it over here, I had the battery with its EMF, the resistor, R, and then the capacitor just acts like a wire. Okay, that's it. The capacitor, I'll draw kind of dashed to remind you where the capacitor would actually be sitting, but if it's uncharged, it has no potential difference across it, so that it acts just like a wire, which is called a short. That's a handy thing to remember then. No potential drop across an uncharged capacitor. You can think of it as just being a wire. Now let's take another extreme. Let's let time go to infinity in the voltage equation for the capacitor. Then I have an e to the minus infinity there. That's 0. 1 minus 0 is 1. 1 times curly e is curly e. The potential difference across the capacitor, so now the capacitor is fully charged, right, as time goes to infinity. And the potential difference across it is the same as the potential difference across that battery. Let me write the EMF here so you can see it. But the only way that can work, if the potential difference across the the capacitor is the same as that of the battery, is if there's no potential difference across the resistor. But the only way you get no potential difference across the resistor is if there's no current. So after a very long amount of time, this circuit acts like there's no current. Well, of course, that's what I just found up there in the graph of the current versus time. It goes to 0 after a long amount of time. Okay? But if I have a loop like this, just a single loop, where there's no current at all, then it's acting like there's an open switch somewhere. And the somewhere is where the charged up capacitor is sitting. So the other thing to note then is when fully charged, the capacitor acts like an open switch. And there's no current in the branch where the capacitor is. Those are two very helpful things there, those statements in red that are in the boxes when you're analyzing a circuit. Okay, now, let's say we've waited a long time, many time constants, even more than 5 time constants. We would then all agree that the capacitor is fully charged. Its charge Q has approached its final value, C times the EMF. Its potential difference across the capacitor has approached its final value, EMF, of the battery, and the current in the whole loop has approached 0, its final value. Now we're going to discharge the capacitor. How are we going to do that? I'll go back up to the circuit. Let me declutter it a little bit and explain how we do that. So after it's been charged up, we take the switch, which remember had been thrown up to point A there, and we throw it down, as it were, to connect the switch to point B, like that. And now the complete loop, you have to look very carefully, consists of these objects. Just the resistor and the capacitor. Note we have effectively isolated the battery. It no longer does anything in that circuit. And instead, what I've got is the charged capacitor, positive charge on the top plate, negative charge on the bottom plate with a potential difference across it, and a resistor, and conducting wire making a loop. So we will have current flow, and it will flow this way. I, counterclockwise. Remember that I'm thinking of the current as flow of positive charge, and I've got excess positive charge on the top plate of the capacitor. So the current flows away from that. Okay? All right. Now, we would want to analyze this kind of circuit now. That's the discharging capacitor. And you could apply the loop rule. That's the physics idea and what we know about capacitance. I'm going to tell you what things you learn. All right, so we suppose then the capacitor has been fully charged to a value of its charge, C times the EMF. And we're going to discharge it. We do that by throwing switch S down to connect to the point B. Note, by the way, the moment we do that, at that instant, we reset the time to time 0. And now we have discharge. And when you have a discharging capacitor, the charge, the current, and the potential difference all just decay exponentially with time, with a time constant tau of R times C. Everything just decays exponentially. Everything. Everything starts at some initial value, at time 0, and just asymptotically approaches 0. You ultimately end up with 0 charge on the capacitor, 0 current in the circuit, and 0 potential difference. Okay? And there are the expressions for the charge and the current and the potential difference. Those are handy. Okay? All right. Now, what I'm going to do next is a little bit of practice with you and then leave you with a class engagement. All right, so there's our standard RC circuit that can be put into the charging configuration by putting the switch at point A, or, once it's charged, into the discharging configuration by putting the switch to point B. And in this practice, we're starting with the uncharged capacitor and charging it up. So, we close the switch on point A so as to charge the initially uncharged capacitor. And then we have a table that has 4 sets of values for the circuit elements, A, B, C, and D. And for each set, there's a value for the EMF of the battery in volts, so 12 volts. For A, 12 volts for B, 10 volts for C, 10 volts for D. The resistance in ohms, 2 ohms, 3 ohms, 10 ohms, 5 ohms, and the capacitance in microfarads, 3 microfarads, 2 microfarads, 0.5 microfarads, and 2 microfarads. All right, A. Rank these 4 sets, A, B, C, and D, according to the initial current, just as the switch is closed on A, greatest first. So I'd like you to pause the video, think about that, and then come back when you're ready. Okay, did you rank the initial current in the circuit? The current at time 0. Well, just start with the current as a function of time for the charging capacitor. I'll remind you what that formula was. That formula, and plug in time 0. You get e to the 0, which is 1, so you get the EMF over R. So the initial current is just the EMF over R. And you get all the values of that for the 4 sets. What's E over R for set A? 12 divided by 2, I think. 6 amperes for set A. What's the EMF over R for set B? 12 over 3. 4 amperes for set B. For set C, we get 1 ampere. For set D, we get 2 amperes. So what's the ranking of the initial currents? There's the biggest, set A. Then set B, then set D, then set C. Okay, that's part A. Part B. Now we want to rank these 4 sets according to the time required for the current to decrease to half its initial value. Well, there's the formula for the current. It's just an exponential decay. Basically, all you got to know is what determines the time for the decay is the time constant, tau. Okay? Remember, tau. And that is equal to, in a circuit like this, R times C. So we're just going to rank the R times C values for the 4 sets. All right, set A, what's R times C? 3 microfarads times 2 ohms is 6 microseconds. That's for set A. What's R times C for set B? 6 microseconds again. Set C, 5 microseconds. And set D, 10 microseconds. So what's the largest time constant? Set D, then A and B tie, then C. Now, I want to explain a little more here. So let me get myself some room over here, in case you're still feeling like I've kind of done a shortcut here answering this. Because what it asks for is the time for the current to decrease to half its initial value. That amount of time is sometimes called the half-life. Let me show you how you could actually calculate that. We know what the initial current is, EMF over R. So, what's half of that? I initial over 2. E over 2R. I want the half-life is the time value when the current is that, E over 2R. So I just go over to the current formula where the I of t is, right there, and I put E over 2R on the left. On the right, I have E over R times the exponential of negative, and now the time is specifically the time called the half-life, so I'll label it T1/2. I can divide out the EMF, I can divide out the R, and the equation really is this: 1/2 equals E to the minus half-life over RC. And I take the logarithm of both sides. Logarithm of 1/2 equals minus T1/2 over RC. Logarithm of 1/2 is negative log of 2. So T1/2 is RC times the natural log of 2. That's a handy way to get the half-life. Just take the time constant, tau, multiplied by the natural log of 2. But notice that log 2 is a constant, and that's why I could answer the question about ranking the half-life just by ranking the time constant. All right, finally, rank the sets according to the final current. Final current after the switch has been closed a very long time. Think about that, please. We got an answer for the ranking. Come back. Okay. Did you say they're all the same? The final current is 0. The capacitor is charging. It's getting more and more charged. The capacitor is getting closer and closer. The current is getting closer and closer to 0. The final current value is 0 in all those cases. So they're all the same. All right, so here's the class engagement. For Blackboard. Got our standard circuit for charging or discharging a capacitor. And in that circuit, the resistance is 2 ohms. The capacitance is 12 microfarads. The EMF of the battery is 10 volts. We're going to close the switch on point A and begin to charge the initially uncharged capacitor. At a certain instant in time, I don't know exactly what the time is, the potential VC across the capacitor is 2 volts. At that instant, what is the current I in the resistor? Okay? It's not a hard calculation. That's what this last statement is. Okay? But you do need to apply a physics idea to the circuit and solve for I. So this means, of course, that you have thrown the switch up to point A. There's a complete loop. You've got a current I flowing that way in the resistor, going around clockwise. What is that I value? That's what you answer on Blackboard. So that's all for the video, and then we'll be talking about RC circuits in class.